Okay, good morning. My name is Rory Fulger. I am a instructional technologist and designer with Wolfram Research. I'm joined here today by Rushank Goyle. Hi, Rushank.
Hello.
So Rushank is a student ambassador with Wolfram. So I'm gonna give him a couple minutes to introduce himself, and then he's gonna go look at some medical image transformations. It's going to be a pretty cool presentation. I'm psyched. How are you doing, Rushank?
I'm fine. It's a good day in quarantine.
Yeah. Great. Do you want to do a quick introduction to yourself before you start?
Sure. Sure. So I'm Rushank Goyal. I study, I'm a freshman at Centennial High School in Maryland, and I joined the Wolfram Student Ambassador Program this year. And today I'm going to do like a live coding session on medical image transformations using some medical data.
Awesome. Go for it.
Sure. So before we go, I just want to give a little background. So there's
Mm-hmm.
basically four types of scans that we'd be looking at. So it's like X-ray scans and CT scans, and then we have ultrasound, so that's just like USG, and then there's something called a PET scan. So I'll basically be showing you the images, then I'll be showing you the transformations that we can do on these. So the purpose of this is basically whenever you're building any kind of artificial intelligence algorithm, you want to highlight the features that are most important, and you want to basically select the features that you think are going to help your algorithm. So that's basically what image transformations are used for.
Right.
Mhm. So let's start with the first example. I have a couple of files here. So I'll just import one of them. Huh, that's weird.
Did you spell hemorrhage right?
Yeah, I did.
It's
That's
always my it's always my question.
okay. It's CD images. My bad. My bad. Okay. This should be. Yes. So as you can see here, we have this CD scan of the brain. So it's usually in a DICOM file, which is like this whole scan. Here we have one section of it, a transverse section.
Nice.
So here, if you see, we have like this whole white area that I don't know how to describe it to you. Like it's a white area, and that's basically something called a space occupying lesion. So it could
Okay.
be a tumor. In this case, it's a hemorrhage, but yeah, it requires medical skill to be able to identify that.
Mhm.
And now, if you want to like train an AI algorithm to do that for you, you really need to know what's important to focus on. So like if you see this area in the middle, that's like in the exact center, that's not really important. That's going to be the same in all patients,
Mhm.
but it could be different because of like genetic variations, and you want to take that out of the algorithm, so the algorithm does not get confused.
Right.
So we're just going to apply a few transformations here. So one of them is contour detect, which is, yeah, we're just going to apply that here. Let me copy this. Point 0.8 is basically the radius. Okay, so you see what we get here is basically this image. And this black area basically tells us that this is something that's odd, that's out of the place.
Nice.
And I do have a normal image here too. Okay. So as you see, what's different in this image is there's no white area, which means patient's brain is perfectly normal.
Mm.
And now if we apply the same transformation to this patient, probably should copy this. So you see, we get a very different image. So
Yeah.
now basically, if we were trying to feed these into an algorithm, they would clearly know the difference because it's like really obvious. And that
Right.
basically helps take out all the differences due to genetic variation. So like one
Nice.
patient might have a different shape, brain, or they might have something else that is not related to what you're trying to diagnose. So that's where
Hmm.
this could help.
Nice. Can I just where did you get all these images from?
Oh, they are usually available in public databases,
Hmm.
and in this case, I think it was like a hospital that's back in India. They agreed to give us these images. They anonymized everything, removed all the details. Yeah,
Nice. Awesome.
although there are plenty of public databases, so you could use those.
Very cool.
Now, this is one of my favorite transformations, image mesh. So if you just put one of these in there, it creates this mesh diagram for you. And so you can see that these areas have been highlighted, the ones in black.
Mhm.
And if you do the same thing now on the other one, there. So it's really different, and
Wow.
an
Yeah.
algorithm could clearly tell the difference. So as I said, the whole point of this is to make these small differences just stand out for the algorithm, so it
Hmm.
doesn't get distracted by all the background noise.
Nice.
I do have a last one, and this is really cool because we'll be applying two functions here. Okay, first I'll show you like just when you just apply one function. So this is gradient filter.
Hmm.
I put that in with a radius of 0.8, and what you get is this. And let me just copy paste that for the other image. Okay, so here, and now there are some differences, but
Hmm.
they're really like not highlighted, and even if you were to see them yourselves or any algorithm, it would be really hard to tell. So this is basically just making the algorithms work harder, which is not what you
Right.
want to do.
Yeah.
So yeah, so you apply this other function, color negate. So as you can see, it's white on black, and there's not really a lot of regions that's white, because what
Hmm.
gradient filter does is basically it uses convolution kernels like Bessel or Gaussian kernels, and then it finds the derivatives of the image, and then it takes the magnitude. So basically, whatever regions of the image have like really fast change,
Hmm.
so like this hemorrhage here, it goes like really suddenly from black to white, that is going to be highlighted.
Right.
And then if you apply color negate, it basically just changes the whole thing. It switches black and white.
Oh yeah.
And as you see, it's much more, yeah, it's much easier to tell the difference now.
Yeah.
So here you have these, like, these are actually like veins in the brain. And
Hmm.
so here they're all normal shaped, but here they're basically swallowed up by this tumor.
Right. Cool.
Okay. So I also want to show one example of how the algorithm can get confused.
Hmm.
So image transformations. Oops, let me remove the gradient filter. Okay, and yeah, I should highlight the image. Okay, so not all image transformation algorithms are going to work on all the images. Like
Hmm.
if you look at then you can see it basically just highlights everything. It
Oh
does
yeah.
not switches. It's all
That's not
changed.
helpful.
Yeah. So you basically have to like understand how they work, and then you have to see how the algorithm could get confused, because
Hmm.
most of them are not originally designed for medical images.
Right.
So you basically have to learn how they work, and then you have to use them accordingly. So as you see, we started from this image, which is kind of clear to understand, but it
Hmm.
has a lot of noise. And
Yeah.
if you see other images, then there can be a lot of variations. If I just show you another one, uh, let's take 42. There. So that clearly has a
Oh yeah.
that clearly has a tumor too, but it has so much variation. and just for good measure, we'll do another one. There, so that's like completely different.
Right.
And if you were training an algorithm to identify those, it would be no good. However, if you like just put whatever we took into here, which was, oops, yes. So as you can see, it clearly has these black spots in the middle. That's
Mhm.
what helps the algorithm identify that this is like abnormal and the patient has to be treated.
Nice.
So this basically highlights whatever you eat. That's basically the ultimate purpose.
Cool.
I do have another exciting like batch of images.
Yeah.
Okay, you kind of need some knowledge for this one. This is called a PET scan.
Cool.
So basically, what doctors do is they give you this, they inject this liquid into you, which is kind of like it shows up on it. The chemical shows up on the
Mhm.
like scanners, and
Nice.
it has glucose in it. So whatever organs use glucose the most, like your brain, your heart,
Uh-huh.
they have a lot of it, and they appear as like black spots. While most other organs that are not as metabolic, they just come there as like white places.
Nice.
And if you have a tumor or cancer or some other form of disease, it's going to be like ready metabolic. It uses a lot of glucose. So it's also going to appear as a black spot. And that's going to be the wrong place because your heart is not in your like whatever legs.
Smart.
So yeah, that's just important image. Let's see. So I have a normal PET scan here. Normal PET.jpg. It could take some time. Okay, there. So as you see, the
Nice.
brain uses a lot of glucose, and that's your heart, and that's your bladder. So these are basically the only black spots that are gonna appear.
Cool.
Although there could be some slight differences, because like maybe you just exercised in there. Uh, yeah. So your muscles are using more glucose, and they could appear black. But
Uh-huh.
mostly, what doctors do is they have you sit still for 60 minutes, and that's how they get consistent measurement.
Nice.
So we're going to use edge detect. So what this algorithm basically does is uh, it sees wherever there are clear distinctions, like this is transitioning from almost completely white to almost completely black, and
Mhm.
that tells it that there's an edge over there. Okay, so as you can see, the brain, the heart, and the bladder are clearly highlighted.
Mhm.
There's some other stuff that's like the amygdala and the other stuff, but
Right.
that's also kind of hypermetabolic, so it makes sense for it to be highlighted. And now I have another one, which is like, so Hodgkin's is basically a cancer, Hodgkin's lymphoma.
Uh-huh.
And I have an image of that, so I'll just show it to you. Okay, so as you can see, if I enlarge this a bit,
Oh yeah.
this person,
That's very different.
it's very different. This person has lymph nodes all over their body, and then all those lymph nodes have been infected by cancer.
Mm.
So it's clearly a lot different. And now if I apply the same function on this one, what I get instead is this whole range of blobs all over the body, because like a lot of areas are black, and it just tells us that they have a tumor all over their body. It's like it's
Nice.
lymphoma, which is like cancer of the limbs, and your limbs are located all over your body.
They're everywhere.
That basically tells us there's an abnormality. And if we just take the same, if we just apply another function called max detect, what it does is it highlights whatever areas are above a certain value. So like
Okay.
the max, you have to put in that parameter. And this parameter, I haven't really talked about this, even though it came up in the last one too, contour
Mhm.
detect. You basically have to figure it out by trial and error, although it does not take long. So you input a few values and you see which one is like clearly which one clearly gives you contrasting regions that you can use.
Cool. Do you know what
Yes.
that value is? Like what it's doing?
Oh yeah, for this one it's 0.6 because I put that in here.
Yeah, but like what is it? Like what's it asking for? What is the variable?
Oh, max detect asks for the radius.
Okay,
No,
what does that do?
like so it asks for a value that's like 0.6, and then it goes through the image and it sees all values that have light intensity,
Okay,
like less than 0.6. So these are black. So they have like they absorb light kind of, so like the light intensity is really low. And that's basically the threshold value.
okay,
As I said, you kind of have to figure it out by trial and error because you don't know how dark like
right.
it would be. Because like this is also dark,
Hmm.
the person center ribs, and but you still don't know how what value to use. So, yeah. There. So if you see these two are clearly very different. So if you would like train an AI algorithm to just use these two, they
Hmm.
would clearly it would clearly be able to tell the difference. This one has
Yeah,
only 3 spots, while this one has like a lot of hypermetabolic regions.
yeah, that's a clear difference.
So this patient, I also have another image of the same patient. So they were diagnosed with lymphoma, and then
Hmm.
basically the doctors gave them antibiotics too, and they used chemotherapy to help them recover a bit. And then
Nice.
they, after 2 rounds of treatment, they scanned. They took a PET scan again. And as you can see, this one's different because in this one he had like lymph nodes, hypermetabolic lymph nodes all over his body, his
Hmm.
or her body, their body. And in this one, uh, now it's changed and it's only around here because that's what chemotherapy does. Chemotherapy kind of affects your other regions, but it also cures the cancer you have. Although the side effects are another topic.
Right.
So as you can see, they have been cured of the disease. Not completely because it's only 2 rounds, but like to a large extent.
Right. Nice.
Mhm.
Very
I
cool.
also have an image of metastasis.
Hmm.
So metastasis is basically, okay, let's see what the error is. Okay, it's a PNG. Yeah, metastasis. Huh. Okay, metastasis. PET. Uh-huh. So
There
as
we
you can see, this is basically like whole body cancer.
go.
This was cancer of the bones. As you can
Right.
see, the bones in the arms and the spine, all of them are hypermetabolic because they're all infected by cancer. So that's basically how you can distinguish between this image and the image of a normal person, just basically just 3 black spots. So again, it highlights the regions of the body that you have to focus on. So as an example, if I were to show you just this image, you really wouldn't be able to tell the like is it normal, is it abnormal. I mean, like you could, but not an AI algorithm, because like each person has a different heart size and they have a different body shape, and those are factors that we know don't really influence the diagnosis, but an AI algorithm doesn't know that, and so it has to be trained that way.
Nice. That makes sense.
Hmm. Okay, so that basically finishes up the PET scan. Should we move on to X-rays?
Sure. Go for it.
Hmm. So X-rays, I do have some X-ray images here. I'm just gonna import them. So CXR basically stands for chest X-ray. Okay, there. This was kind of a big image.
Yeah. Nice.
Okay, so as you can see, this is basically a chest X-ray of a person. This is like a normal person, what their heart would look like, and their organs below that.
Cool.
Let's just copy this for later use. And now there's another image of this disease called cardiomegaly, which is basically like your heart grows bigger. So that's
Okay.
a disorder. And one of the good things I found out about Wolfram was that it's not like some other languages that only allow you to use JPEGs and PNGs. So
Uh-huh.
JFIF is usually the format that these files come in, and it's really a pain to convert them. And I was kind of pleasantly surprised when I saw Wolfram put directly imported.
Nice.
I wanted to point out.
We always
Okay,
aim to pleasantly surprise.
thank you. Okay, so as you can see, the heart has grown bigger. So
Yeah.
that's basically the disorder. And now there are a lot of variables that are different. For example, if you notice in the first image, we have these person's arms that are showing in the background, while
Right.
not in the second image because it's basically a different section.
Uh-huh.
Also, their heart growing bigger just makes the body less intense because like it has to balance everything. So it,
Right.
like everything is relative for the image when it creates that image. And I do have another image here. I think it's CXR normal too. Yes. This is also a large image, so it may take some time to render.
Nice. No
Okay,
worries.
so this is also another image of a normal person. And if we compare it to the image of another normal person, even people who are normal clearly have a lot of differences, and that's
Right.
just because they're all human. But any algorithm only needs to focus on what's important, and that's recognizing that there's a heart disorder, basically. So again, we use the function max detect. And this value, again, it has to be found by trial and error, 0.25. Okay, yeah, this is a large file, as I said. Okay, so as you can see, max detect has like taken the areas that are, pardon me, yeah, max detect has taken the areas that are like white and it has enhanced them, while everything else that is below a certain threshold value of line intensity, they have like faded into the background.
Nice.
And let's just apply this to the normal image, the second normal image. So if you were an AI algorithm, you could kind of see the similarity between these two, right? Much better than you could see in the original image, because they both have like this center area of white, which is the spine,
Right.
and these ones on the end, which is like the rib cage.
The ribs.
And so that kind of makes it more obvious. And then the key thing you do is basically, I just copy this for yeah, cardiomegaly. Yeah. Okay, so this is clearly much different because the
Yeah.
heart is bigger. So there's this huge region of white. And now you might wonder why these, like the rib cage is not appearing. As I said, when the X-ray machine renders these images, there's only a scale it can go, like a monochrome scale.
Right.
So if the heart becomes like brighter, the other stuff has to become dimmer to compensate.
Right. That makes sense.
So yeah. So now if you were to apply these transformations and feed these images into an AI algorithm, it would be like much clearer. And it basically highlights the important regions,
Nice.
which as I said is the use of these image transformations, other than for fun.
Sweet. I love it. Very
I
cool.
also have another one.
Please.
So this is basically an ultrasound. Yeah, ultrasound is basically like there's a special machine and you apply a gel and then
Uh-huh.
you basically get an image of the person's abdomen. Okay. Okay, it's liver normal PNG. Okay, liver USD normal. I'm not good at naming files, as you can see. Okay, so it's really not clear. It's quite blurry, but that's just what the imaging technology is.
Right.
And it's our job to apply image transformations to somehow make that clearer. So this is the image of the liver of a normal person, which is like, as you can see, there's nothing that stands out of the ordinary.
Mm-hmm.
This area in the right, that's just the liver.
Cool.
Okay. Liver cyst. Okay, this this image, as you can see, is quite different.
Right.
So there's basically a cyst that's an outgrowth in the liver.
Mm.
And there's some other images of a tumor. I'll just put them here. Okay. Okay, so here, this is again different from the normal one, because here you see it's just like a normal image with no abnormalities. While here, there's this ring that clearly stands out. So these are subtle differences, and again, we need to apply image transformations to make these more obvious. So for this one, there's a special filter called the Cardiomegaly filter.
Uh-huh.
So if I just import this image for once. And again, there's these values that have to be kind of found out by trial and error.
Mm-hmm.
20 and 0.005. It takes a while to transform the image. Okay, but as you can see, this has kind of become more blurred. And now, like any normal person would say, how does that help? That just makes the image more blurred, which is kind of true. However, now if you go to the one with the tumor and you apply the same transform, also okay, it's JPEG. Also, I did not discuss these values. So 20 and 0.005.
Mm-hmm.
0.05. So basically, I want to emphasize the consistency. So like these values here are 20 and 0.05, and these ones here are also 20 and 0.05. If you see in our other examples, the value has always been the same, 0.25, 0.25, and 0.25. And as the last example, I'll just show this one, 0.8, 0.8, and
Nice.
0.8. So there's basically this value that you kind of have to determine. But then it's important to keep the value the same, because like if you have 300 images and you just know that the value is here is 0.6, so you can just apply 0.6 to all of them.
Right.
Max detect with 0.6, and it's going to give you like accurate results, because you cannot go and figure out the value for each one of them. That's just a waste of manpower and also impossible. Okay, so if you apply the Cardiomegaly filter to this image, but you can see that this has also become blurred. However, these regions here, the tumors in the center,
Mm-hmm.
they become more blurred than usual, because they're kind of like separated by this black line. It
Right.
just kind of marks this area of rapid change.
Mm-hmm.
So there's this conductance value that we put in here as the parameter. So a large conductance value, what it does is basically it only preserves like really strong edges. So in the normal one, there really were no edges, so it basically just blurred everything. while here we had these really strong edges, and so it kind of had a different effect to them, and that highlights it. So now if you put all these images in an algorithm, the normal ones don't have anything, they're just blurred images, while these ones have these special regions in the middle.
Mm-hmm. Nice.
And if you also apply this to the third one, liver cyst, so that's just a cyst in liver. So this is clearly quite different again.
Yeah.
So if you were to make an algorithm that is trying to classify whether the person is normal, which is good, it's extremely good,
Mm-hmm.
and if the person has uh, a tumor, which is not that good, and if a person has like a cyst or an outgrowth, which is less worse than a tumor, but it's still not as good as normal. So there's
Right.
basically these three categories that you can put them in. And it's kind of important to know if a person has a tumor or if they have a cyst, because there's going to be different treatments for each one.
Right.
And sometimes it's just fine to make it like normal or abnormal, but other times you have to like specify. You have to find out some filter that specifies whatever categories you want to put them in. Going back to this example, so here this person is normal, and
Mm-hmm.
this person, like after the filter, this person has like Hodgkin's, which is first stage cancer. This person is normal, and this person has metastasis, which is second stage cancer.
Okay.
So again, it puts them into three different categories.
Nice.
Uh, Also, I want to kind of stress the importance of just messing around with these image transformations, because
Mm-hmm.
there's really no definitive answers as to what image transformation always works. It always depends on what kind of images you have and what the goal you have in your mind. So there's this spectrogram, which is usually not used for image data, but
Okay.
let's give it a try anyway. At least that's what I thought when I was. It just takes a few values, functions to get the data in shape. Okay. This could take some time. Okay. So as you can see, we get this kind of image that really has no meaning on its own.
Right.
But if you were to compare that to some other one, okay, it's JPEG. I remember it by now. There's this one. So, okay, you can clearly see they're really different.
Yeah. That's
Although we
real
not
different.
apply any like meaningful transform, because like this is not something you would usually go to as a first choice.
Mm-hmm.
But if you just kind of keep experimenting, you can find out whatever differences these images might have. And these differences are mostly because of like the colors of the images. And
Right.
yeah, that's mostly because of. So this has large black regions, and
Mm-hmm.
this one the difference is not that prominent. But what I'm trying to say is you never know what could be helpful. So like if you were to build an algorithm based on these images,
Mm-hmm.
it's clearly like it's even easier than using the images themselves. So yeah, that's just another thing.
Nice. I like it. Um.
So yeah, that's pretty much all I wanted to show. We had quite a lot of images. We
Yeah.
applied things to them, and we showed how they could fail sometimes and the importance of like, just trying different algorithms and seeing which one works. And also, you don't always have to do trial and error. You can just reason that because this one, like this image has large areas that stand out, maybe edge detect would be a fit for it, or contour detect. So yeah, you can
Right.
reason like that. It's not all trial and error.
Yeah. That makes sense. There's definitely some
Yeah, there's definitely a lot of science involved.
pre-thought. Yeah. Yeah.
And I mean, if you were to find out like, if you were to actually measure the, so like here, if you were to actually measure the intensity, like the light intensity,
Uh-huh.
then you would not have to guess. You would just know that it was zero point 0.6. And like that's what differentiates the black regions from the gray ones.
Okay.
So yeah, although that's like beyond my scope.
That's fair. Yeah.
Mhm.
Um. Okay. There are a couple of chat questions. Do you wanna? Should we have a look?
Sure.
So one of the first ones is what is the difference between a threshold and the max detect function? Can you talk about
Uh,
that?
Threshold functions, we didn't really use the threshold function.
Yeah, but like the thresholds. So the max detect takes a radius, right? That does threshold.
Yeah, so
That is a threshold.
I get that. So you can just apply max detect to an image without providing this, although then it basically tries to like find a value that it thinks will fit. Uh, okay, here basically h is where the range of values is not greater than h. So it finds like the maximum, like
Uh huh.
maximum, which is basically the plural of maximum. So it finds those regions and the value is not greater than h. That's basically what max detect does. And this I kind of refer to as the threshold, although I don't, that's not the technical term. It's basically, yeah, it's basically a value above which you can, above which, how do I kind of put this? It's a value above which the the areas are in the image and below which the areas are out. So it's like black and white. So these areas happen to have a value which is larger than zero point 0.6, and
Uh huh.
so they're in the image, and the gray ones are just out because they have a value that's lower than it. So it kind of just removes them.
Okay, sweet. That makes sense. That makes sense.
I hope my explanation was like usable.
Yeah. Um. Okay, we have a kind of sidebar question that's not necessarily completely related, but uh,
Mhm.
Steve has asked which functions, in your view, are useful in detecting whether images have areas that have been like doctored by Photoshop or other photo editing software. Like, so as a kind of extension of this.
Oh, okay. Yeah. So you basically want to figure out if the image has been photoshopped.
Yeah,
Uh,
yeah. How would you go about looking through that problem?
hmm. I guess if somebody photoshops an image, so there's this known bug in Photoshop where if you blur it, like applies the square root function before blurring, and that's like basically this. It applies functions in the wrong order because of how computers store images,
Okay.
and that makes an area of black around the blur. So if I were to like get this, this is basically pink. So if I were to blur this image somewhere, it would
Mm-hmm.
create this black region around it because that's a bug in Photoshop. And so if somebody were to apply that and then you were to pass it through maybe the Perona Malik filter, which is basically used for like this black region around this, it's been highlighted. So maybe that could help.
Nice. That makes sense. That could be cool.
That's basically, there's not many ways to detect because if you're going to Photoshop something, you're going to be really careful about not leaving any clues.
Right. Yeah.
Though you
Good
could expect,
photoshoppers are maybe hard to detect.
yeah, yeah, it's usually hard to detect.
Yeah.
Although if there's a bug like this one, it can help.
Yeah. Sweet. Um. So you're doing a project, right, with medical images. So
Mhm.
now that you've looked through all of these kind of image transformations, like what are your plans? What are you aiming to do in your project?
So before this, I did have the images and I tried to put them through the algorithm and train them using different methods, building different networks.
Uh-huh.
And for some reason, it would never be up to the accuracy that I wanted. And then someday I just stumbled upon these image transformations by like looking into feature detection and stuff.
Right.
And then I basically started experimenting and everything. So now that I know like how helpful these can be, they basically isolate the most important regions for you, as you can
Uh-huh.
see here. in all the other examples we did. So I'm probably going to find whatever transformation works best for my images and then apply those, and that will hopefully give me a higher accuracy.
Nice. Nice. So you're making a kind of machine learning diagnosis tool.
Yeah, oh yeah. I think I only told this to you. The other people might not be familiar. I'm basically making this tool where it's concerning hemorrhage. So that's why I had these images of hemorrhages, normal and hemorrhage. So you put in an image and it tells you if the person has a hemorrhage in his or her brain. So that's an AI tool for that, to reduce doctors' workload and stuff.
Great. Awesome.
So that's also why I put this in my examples. Because like if I apply the transformation I showed you, it's going to make it really easy for the algorithm, and it's going to give like much better accuracy.
Sweet. Okay, is there anything else you'd like to share with us?
I just wanted to mention that blur bug in Photoshop, and like kind of a pleasant surprise. I got that in a question. So
Nice.
yeah, that's like really a 1 in a million coincidence. There's this specific bug I want to talk about, and somebody asked about it in a question.
We're on your wavelength.
Yeah.
Okay, great. Well, thank you so much, Rushank. And a couple of people in the chat have said thank you, and it's been pointed out that it's a really tough thing to do a live stream, and even for the seasoned pros. And you've done a really, really good job.